Welcome to Pneumatic. In this video, we're going to solve another exercise in the series of exercises related to the concept of a viewing in motion of objects within accelerated frame of reference, either from inertial or non-inertial frame of references. So the introduction to such concept of a frame of references was explained in a previous video, which you have to check it before solving such exercise. In latest video, we solved this exercise, where we want to study the motion of a pendulum within accelerated trolley, and we want to calculate the angle of inclination of the pendulum from its original vertical position, given that the acceleration equal to a. So we apply the Newton's second law on the pendulum along both axes, and we get that the alpha equal to angle of inclination equal to shift tangent a over g. Now, in this video, we also need to calculate the angle of inclination of the pendulum, but we don't have the value of acceleration directly. Actually, we have an additional detail in this question, that there is a block in front of the accelerated trolley that is not sliding with respect to the trolley. We will see that we can deduce the value of acceleration by applying a Newton's second law on this block, so that we have the value of acceleration and we deduce the value of alpha. So the question states that a trolley A has a simple pendulum suspended from a frame fixed to its desk. A block B is in contact on its vertical side. The trolley is on horizontal rails and accelerates toward the right such that the block is just prevented from falling. The value of coefficient of friction between A and B is 0.5, and he is asking to get the angle of inclination. Now, first of all, since we want to study the motion of objects, in this case a pendulum and a block, within accelerated frame, that is a trolley, then we can study their motion from two frames of references, either from an inertial frame of reference, that is, the observer is observing the motion from the ground, or from non-inertial frame of reference, where the observer is observing the motion from within the accelerated trolley. Okay, for case 1, viewing the motion from inertial frame of reference. So here, since no motion between the block and the pendulum within accelerated frame of reference, that is, block not sliding relative to the trolley, and the pendulum is fixed at its final position, then the observer is observing the accelerated trolley and the pendulum and the block as a one system. So the pendulum and the block also have the same acceleration as the trolley. So since he is asking about the inclination of the pendulum, then the first step we should do is to apply Newton's second law of motion on the pendulum. First, we project the force along the axis of motion. There is tension T, which make with y-axis angle alpha same as the angle between the pendulum at its final position and the original vertical position. And tension T can be projected along the x-axis, so we have Tx equal T sine alpha, and projected along the y-axis, so we have Ty equal to T cosine alpha. If you didn't know how we deduce Tx and Ty, here is the explanation on this figure. There is also weight force, an mg, directed entirely along the y-axis downward. So according to Newton's second law, along the x-axis, we have T sine alpha equal to max equal to ma. Acceleration is entirely projected along the x-axis, so ax equal to a, which is the acceleration of the trolley. Along the y-axis, we have summation of force along the y-axis equal to 0, so T cosine alpha equal to mg. Then by dividing the equations, equation 1 by equation 2, we get tangent alpha equal to a over g. Then alpha equal shift tangent a over g. So in order to get the value of acceleration, we have another object on the front of trolley. So let's apply Newton's second law on it. Force along the box, we have weight downward along the y-axis, and the normal force made by trolley on blocks toward the right, and the friction of upward direction. Now along the x-axis, summation of forces equal to ma. Then normal force equal to mass of the box multiplied by acceleration, which is equal to acceleration of the trolley. Along the y-axis, summation of force is equal to 0. Then the friction equal to mg. And we know that the friction equal to coefficient of friction, which is mu, multiplied by normal force n. So we get mu multiplied by n equal mg. Then normal force equal to mg divided by mu, which is the coefficient of friction. Now we replace the value of normal friction by substituting equation 2 by equation 1. And we get that acceleration equal to gravity over coefficient of friction mu. Now we have the value of the acceleration. So we substitute it with the equation of inclination of the pendulum alpha. And we get alpha equal to shift tangent g over g multiplied by coefficient of friction mu. Gravity and gravity are cancelled, and we get that the alpha equal shift tangent 1 over mu. And we have coefficient of friction mu equal to 0.5, then alpha is equal to shift tangent 2. So the right answer is B. Now, other way to solve this type of question is to observe the motion of the pendulum and the box in accelerated trolley from within the accelerated trolley itself, that is, from the non-inertial frame of reference. Now remember that in observing the motion from accelerated frame of reference, you must assume the presence of pseudo-force. So for both pendulum and the box, since they are not moving with respect to the accelerated frame of reference, which is the trolley, and we are viewing the motion with respect to this trolley, that means they have zero acceleration with respect to the trolley. Applying Newton's second law on pendulum, we have tension T projected along the x-axis and the y-axis, as we have seen in case 1, Tx equal T sine alpha and Ty equal to T cosine alpha. Also there is weight downward, plus there is a pseudo force, which direction is opposite to the acceleration of a trolley, and the value equal to mass of the object, which is in case the pendulum, multiplied by acceleration of the frame of reference, that is acceleration of the trolley. Now along the x-axis, summation of forces equal to 0, as we state that acceleration with respect to the trolley of these objects is equal to 0. So we have T sine alpha minus pseudo force equal to 0, then T sine alpha equal to ma. M is the mass of the pendulum. Along the y-axis, also summation of force equal to 0, there is no motion along the y-axis. Then T cosine alpha equal to mg. We do the same thing as before. We divide equation 1 by equation 2, and we get alpha equal shift tangent a over g. To calculate the value of acceleration, we apply Newton's second law on the box. We have normal force made by trolley on box toward the right, and weight force downward, friction upward, and the pseudo force backward opposing the direction of the acceleration. Now along x-axis, also summation of force equal to 0, then normal force minus pseudo force equal to 0. So we have normal force equal pseudo force equal mass of the box multiplied by acceleration of the frame of reference, that is acceleration of the trolley. Along the y-axis, we have summation of forces equal to 0. Then friction equal to mass of the box multiplied by gravity. Friction equal to coefficient of friction multiplied by the normal force equal to mass of the box multiplied by gravity. Then we get the normal force equal to mass of the box multiplied by gravity over coefficient of friction. We do the same thing as in case 1. We substitute equation 2 in equation 1. So we get acceleration equal to gravity over mu. So now we have the value of acceleration, and we substitute in the equation of alpha. We get that alpha equals shift tangent gravity over gravity multiplied by mu. That is alpha equals shift tangent 2, since the coefficient of friction value equal to half. Same answer as case 1. So in this exercise, we view the motion of the pendulum and the box that are placed in accelerated frame of reference, that is the trolley. And we get the inclination alpha of a pendulum at its final position with respect to its vertical position by applying Newton's second law on the pendulum, and we deduce the value of acceleration by applying Newton's second law on the box. And we viewed their motion either from an inertial frame of reference where the observer was standing on the ground, or from non-inertial frame of reference where the observer is observing the motion of these objects from within the accelerated trolley. And that's it. Stay safe.